Hey, we're going to get started on 5.3 notes. Just let me share my screen. All right. So 5.3 is all about linear versus exponential and logarithmic. So we're looking at defining new functions called exponential and logarithmic, but we're going to compare it to something you know very well, and those are linear functions. A linear function adds a fixed amount to the previous value of y for each increase in x. So, for example, in a linear function, let's say we have this function 10,000 plus 500 for every x. So, 500 is added to the y for each increase in one x. For exponential, it multiplies a fixed amount by the previous value of y. So, for example, we would have 10,000 times 1.05 to the x power. So y is multiplied by 1.5 for each increase of 1 in the x. And so when we're looking at this, it's really important for you to be able to distinguish between which one is linear and which one is exponential. So this first section is just, can you do that? So we know linear functions are written as y equals mx plus b, or in some ways, you might find it as f of x equals ax plus b. Either way, you have a slope or a rate of change, and you have a y-intercept. Okay. Your slope is multiplied by your input, but it's added to that rate of change. I'm sorry, to that initial value of that y-intercept. And so this formula, the formula for exponential is different because the exponent contains the x term. So that's why it's called exponential. And this function is this. So you have a c value, which is the coefficient, and then the a value, I like to call it the growth rate. It's kind of like slope, but it's the growth rate. And then notice that the exponent is where your x is. Okay. Now we're going to get into, can you define and determine which one is which? So identifying f as being linear or exponential. And so for part A, we're going to say that this is linear. And the reason this is linear is because we have our rate of change and we have our slope, and they're added together. Whereas part B, this is exponential. And first off, the exponent is in the x. It's the exponent. But then also the growth rate is multiplied versus here it's an addition. And I think another way to see this is that when you have repeated addition, that's how we're going to have our slope realized. Like you're just adding the same value over and over and over again. But when you have repeated multiplication, that growth is so much faster. And that's when our exponentials come in. So let's look at an example from a graph. So our initial value was -3. And after the first iteration, we see that we have an increase of 1.5. In the second iteration, it's an increase in 1.5. And the third, it's an increase of 1.5. So for every change in x, there's a constant change in y. So for each unit increase in x, the y value increases by adding 1.5. So these data are linear. And then when we look at our exponential or our next graph, table, you can see that for every increase in x, we have this being, it's getting smaller by a factor of 1/4. and another factor of 1/4. 4 times 1/4 is 1. 1/4 times 1/4. I'm sorry, 1 times 1/4 is also 1/4. So this time we are multiplying by 1/4. So these data are exponential. Okay. So now I want to kind of go back and see what the equations would be. It's super simple, and I can show you where the parts for the equation come from and how they're realized when we have a table. So for this first one, we're going to say we know it's linear, so it should be f of x equals mx plus b. And we need to know our rate of change. And the rate of change is the change in y over the change in x, or the change in the output over the change in the input. So in this case, it's 1.5 for every x plus our initial value, which was -3. And so to clean that up just a little bit, we'll have that f of x equals 1.5x minus 3, where this is our rate of change. This is how the graph is changing. And then this is where it begins, so the y-intercept. Okay. And for the exponential, you'll kind of see a similar situation happening here. The formula in this case is f of x equals c times a to the x. So f of x equals, the c is going to be the initial value, the y-intercept, okay? And that's here 16. I also call it initial, the beginning value, okay? Okay. Times our growth rate. So this value is going to be, how is this thing growing? It's growing by a factor of 1/4, which means it's actually decreasing. And then the exponent is in the, I'm sorry, the x is in the exponent. And so there you have your equation. Okay. Okay. So this is just a concept table to where you can kind of take this away and see what it looks like differently. So comparing linear to exponential, notice that there's always going to be an addition on the linear when we're talking about our constant rate of change. And in a graph, you can see it gradually growing by that same amount. So it's going 2 up every time. It's an increase of 2 every time. And that's what that looks like. Whereas if it's exponential, it's multiplying by a value. And so the previous value is going to be multiplied by 2. So let's say this first value is 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So we're not just adding 2 every time to where it's a constant straight line. It's going to get faster a lot quicker, because 8 times 2 is 16. Then we get to 32, and then we get to 64. And so you'll see that this kind of shoots off exponentially. Okay. I love exponential functions because they remind me of love. You meet someone and you kind of like them. You're kind of cool. Okay. Hey, how you doing? And then after the second day, after the first day, it's like, okay, I'm feeling them a little bit. Then y'all go on the first, maybe your second day, and you're like, okay, this person is my person, kind of, maybe, I don't know. You don't want to go too crazy. And then the more and more you spend time with them, like it's just off from there. Just love. Love is growing exponentially. Maybe it's not the case, but sounds good for the hopeless romantic. All right. So example 3 is going to give us an opportunity to just put these parts together. So we have, it says find C and A that satisfy an exponential graph. So when x is 0, y is 4. When x is 0, y is 4. So if we were to draw that on a table, that's our y-intercept. This is the beginning. At the very beginning of the graph, y is 4. That's our y-intercept. So that is our c value. So c is 4. Because the y-intercept is whenever x is 0. Okay. Finding A is pretty simple because all we have to do is find out how is this thing growing. So this is the increasing factor in this case, or what I like to call it, the growth rate. Okay. So from 0 to 1, we have that increase, but here we're multiplying by 2. So because we went an increase from 4 to 8, sorry, y'all. All righty. Sorry, y'all. Did not expect that to happen, but it's all good. All right. So because we have the y value increasing from 4 to 8, then therefore we know that we're multiplying by 2. So that means our a value is 2. So when you put all this together, if this is our formula, I'll just pick f of x. Then we have 4 times 2 to the x power. And that would be our equation. So here's another example. Example 3, part B says, let's write it another one when they give us the verbiage. Even when they give us the verbiage, I like to still make a table. So it says there are initially 600 bacteria and the number doubles each hour. So starting with 0, I have 600. After the first hour, it's going to double to 1200. And then another hour, it's going to double more. So 2400, 4800, and so on. So when I'm writing this out, my initial value is, C is 600. That's what I started with. And it's doubling. That means 2. So f of x equals 600 times 2 to the x power, where x is the number of hours. Okay. Here we have the verbiage again. It says there's initially 50 bacteria, so that's my C value, and the number decreases by half. So that means we're multiplying by 1/2. So the growth factor is just 1/2. Okay, so it's just, if you want to see it in a table, at the initially you had 50, first hour you have 25, second hour you're going to have 12.5, the third hour we're going to have 6.25, and so on and so forth. Okay, so when you put it together, we're going to say that f of x is equal to 50 times 1/2 to the x. Now I just want to pause right here and notice that when it's getting larger, the values are getting larger, this value is greater than 1. But when the values are getting smaller, decreasing, notice that we have a fraction, a number less than 1. Okay. So let's look at this one more time. This time we're going to be dealing with percentages, and I need you to pay close attention to this so that you understand how to work with those percentages. So our initial is 2,000. We already got that. We have 2,000 bacteria. The number is increasing by 25%. The easiest way to work with percentages is to always know that a whole is 100%. So if it's increasing by 25%, we're going to add 25 to it. So that's 125%, because 100 is basically you're going to keep what you have. When you increase by 25%, you have to have an additional 25%. So that's why we have 125%. And of course, when we're working with decimals, which is how you want to write your factor, your growth rate, we're going to say 1.25. That's our growth rate. It's greater than 1, because if it was just 1, we'd have the same amount every time. So when it's greater than 1, that means we're increasing, just like we talked about right here. That number is greater than 1. It's increasing. When that A value or that growth rate is less than 1, we have a decreasing of value. So because this thing is increasing, we know that our value is going to have to be greater than 1. That's going to be that 1.25. So our function is 2,000 times 1.25 to the x. Okay. And of course, in this case, is x is weeks. Part E, we have a 300 bacteria initially, and the number decreases by 20%. So we have our 100 if we were to just keep the same value, but instead we're decreasing. So we're going to subtract 20. So that's going to give us an 80% rate of what stays. So therefore, we're going to have 0.80 as our rate. So when we write this together, we start with our 300, and then the factor is 0.80 to the x power. And of course, you could just write this as 0.8. You don't have to have that extra 0 on the back. And in this case, x is number of years. So when you're decreasing, you're going to subtract the percentage that you're decreasing by. And if you are increasing, you'll add the percentage. And that's how you'll come up with your rate. All right. Graphing exponential functions. So this is what we were just talking about. When the a value is greater than 1, your function is going up. So all of these are going up. They're increasing. Okay. Whereas when the value is between 0 and 1, so less than 1, but like it's still a positive number, that value is going to be decreasing. And when you know the shape, you can kind of just use different points on the graph to be able to draw that graph. So decreasing says, hey, it's coming from the top and just going to flatten out. So notice that these all flatten out. That's called an asymptote. We talked about that in a previous section. An asymptote at y equals 0. So exponential growth, there's an asymptote. Exponential decay, there's an asymptote. So it's never actually going to make it to 0, but it will approach it. So growth, when the a is greater than 0, that's called a growth factor. And then if it's between 0 and 1, that's called a decay factor. So when we talk about what the domain is, this thing has arrows to the left, to the right, and no restrictions. So our domain for an exponential is all real numbers. The range, however, it actually has a restriction because it will never cross this x-axis. So it's going to be strictly from 0 to positive infinity. And notice that I didn't include the 0 in the set. And the reason is because it won't actually touch 0 because there's an asymptote at y equals 0. Now, is it continuous? Yes. No breaks. Is it 1-to-1? Yes. Each x value has its own y value. Or I can say, instead of saying y value and x value, I'll say each input has its own output. So in this case, like if I put a -1, it's going to be like, let's say that's positive 1/2, and then 0 is 1. And then, so each one has its own value. This value will never be repeated again. Whereas like a parabola, it's not 1-to-1. Because there's symmetry. So the same value is appearing on either side of the parabola. So there's two numbers that are going to have the same output. But in this case, that's not the case. So this one is 1-to-1. And because it's 1-to-1, it does have an inverse. Okay. So let's see if we can look at this from a graphical standpoint. It says use this graph to determine the values for C and A. So C is where it crosses the y-axis. C is the y-intercept. Okay, so in this case, C equals 3 because this is the point 0, 3. Okay, now to get from one point to the next, that's what we need to figure out so that we can kind of determine our growth rate. So I see another point here at 1, 3. I'm sorry, 1 and 1.5. It also gives us a point back here. Oh Lord, that's not 1. This is 1, so this is 0.5. But they also gave us a value right here where it's negative 1/2, 6. So we can use these values to try to figure out what our growth rate is, okay? So the value that they gave us was the negative 1/2, 6. Well, if we use our formula, okay, we know that our initial value is 3. We don't know our A, but we have an X and we have an F of X. So our X is negative 1/2, and then our output was 6. So let's solve for A. Okay. So divide by 3 on both sides, and we'll have A to the negative 1/2 power is equal to 2. The only way to, this is algebra, so we have to like really use some algebra here. The only way to get to this A and get A by itself is to raise this to the negative 2 power. That is because negative 1/2 times negative 2 over 1 is going to make positive 2 over 2, which is 1. We want our exponent to be 1. So it's always the reciprocal and then make it positive. So if it's negative, multiply by negative. If it's positive, stay with positive. So keep the sign. And so you're going to do that to both sides. And 2 to the negative 2 power is just 1/4. And you should remember that from algebra 2. A negative exponent is the same thing as 1 over that exponent positive. So this is just 1/4. Okay. So we have A is our 1/4. So now we have A and we have C. And so we can put it together and we're going to go with f of x equals 3 times 1/4 to the x. All right, now we're getting into the application problems, and these are going to be really important for the exam. So I would say definitely start this and get it together. So we can find the amount of money that an account holds. That's A, the amount of money in an account, given like that we are growing this money using interest. So principal is the amount, the initial amount that you started with. And then R is the rate. N is the number of times per year that we are compounding it, which means that we're applying the interest. And then T is the number of years. Okay, so let's just do a practice problem. It says, suppose $1,000 is deposited. So that's our principal. We have $1,000 initially by a 20-year-old worker. Well, that doesn't really come into play just yet. In an IRA, it pays an annual interest rate of 12%. That's 0.12. You always want to write your percentages as a decimal. Describe the effect of the balance after 45 years. So 45 years passed, the person's now 65. We don't actually care about that, their age, because it tells us the number of years. Okay. Uh-oh. Uh-oh, hold on just a second. My computer is frozen, so let me just bear with me for a second.